Welcome to The Explainer. Today, we are diving deep into the one feature that really makes Apache Kafka so powerful and ridiculously scalable, the consumer group. So let's kick things off with a problem I'm sure you've bumped into or you're about to. You've got a single service, and it's trying to drink from a fire hose of data. It's just not working, and you've got a massive bottleneck on your hands. You see, when you've got just one consumer trying to handle every single message from every partition in a topic, it just can't keep up. It gets overwhelmed fast, and your processing just falls further and further behind. But what if that lonely, overworked consumer could, phone a friend for backup? Well, it turns out Kafka has this really elegant, built-in solution for exactly this problem. And it's called a consumer group. The magic here is actually super simple. You just launch multiple copies of your application, give them all the exact same group ID, and boom. Kafka automatically recognizes them as a team and starts splitting up the work between them. Right, so the main thing to get here is that any consumer with the same group ID is on the same team. They're all working together to process data in parallel. It's basically free built-in load balancing. But how does Kafka actually decide who gets which piece of the pie? Well, it all boils down to one fundamental rule that controls this whole system. If you get this one rule, you've basically mastered how to scale Kafka consumers. It's that important. And here it is. This is the golden rule of Kafka consumption. A single consumer? Yeah, it can totally read from a bunch of partitions at once. But a single partition? Nope. It can never be read by more than one consumer from the same group at the same time. And if you think about it, this makes total sense. It's like a grocery store, right? The partitions are the checkout lanes, and your consumers are the cashiers. You just can't have two cashiers ringing up items at the same register. It would be total chaos. This rule prevents that mess. And way more importantly, it's what guarantees that messages inside a single partition get processed in the exact order they should up. Okay, so let's walk through a few scenarios. What happens if you have fewer consumers than partitions? Like here, 6 partitions, but only 2 consumers. Is that a problem? Not at all. It works just fine. Kafka just divvies up the work, so each consumer is now responsible for 3 of those partitions. Easy enough. Okay, now this is the sweet spot. This is what you're often aiming for. When the number of consumers lines up perfectly with the number of partitions, that's when you hit peak performance, maximum parallelism. Every consumer has exactly one partition to focus on. It's clean, it's efficient. But look what happens if you get a little overzealous and you spin up more consumers than you have partitions. Well, because of that golden rule we just talked about, those extra consumers, consumers 7 and 8 right here, they literally have nothing to do. They're just sitting on the bench, idle, burning CPU cycles, and costing you money for no reason. So this all leads to a super simple but really powerful formula you've got to remember. Your maximum level of parallelism for a single group is always capped by the number of partitions in that topic. End of story. You want more processing power. You need to add more partitions first. Now, this system is amazingly flexible, right? You can add and remove consumers whenever you want. But, and this is a big but, that flexibility comes with a price tag, a hidden cost that you absolutely need to be aware of. See, anytime a consumer joins the group or leaves, maybe it crashes or you just shut it down, Kafka kicks off something called a rebalance. And what that means is a stop-the-world pause. For a moment, all processing for that entire group stops dead in its tracks while Kafka reshuffles the deck and hands out the partitions again fairly. And that little stop-the-world moment, it might only be a few seconds, but if you're handling thousands of events a second, that's a big deal. It can create a backlog that takes minutes to clear. And that's exactly why having unstable consumers that are constantly crashing and rejoining or scaling up and down too often can really hurt your overall throughput. All right, so we've seen how consumer groups let us scale one application. But what if you have multiple, totally different applications that all need to read the same stream of data? How does that work? This is where that little group ID becomes your master control switch. We already know that if consumers have the same ID, they're a team, and they share the work. But if you give a new set of consumers a different group ID, well, they become a whole new team. They get their own independent copy of the entire data stream right from the very beginning. And this right here, this is the classic pub-sub pattern in all its glory. You have one orders topic. Your analytics service, in its own group, can consume every single order. And at the exact same time, your notification service with a completely different group ID can also consume every single order. They don't even know the other one exists. They're totally independent. Okay, so here's a pitfall I have seen happen way too many times. Developers give their different microservices the same generic group ID, something like processors. And what happens? They accidentally start load balancing with each other. Your analytics service gets half the orders, the billing service gets the other half, and suddenly your reports and your invoices are both completely wrong. It's a mess. So let's wrap this all up. It's super simple. Same group ID, you're sharing the work. Think load balancing. Different group ID, you get independent copies of the data. Think pub/sub. And always, always remember, your max parallelism is tied to the number of partitions, and scaling in or out causes that rebalance pause for the whole group. Master these concepts, and you've mastered Kafka scaling. So now you know how to scale your consumers like a pro. But how do you make sure that if one of them crashes, it can pick up exactly where it left off without losing or reprocessing data? That is a fantastic question. The answer is all about managing something called offsets. Basically, the group's bookmark in the data stream. And guess what? That is exactly what we're going to break down in our next explainer.